So guys, in today's session we will be starting ISRO 2016 question paper. That is a solution of fluid mechanics and hydraulic machine. So we will move on to the first question. Yes. Now read the problem. Here air is accelerated through accelerated isentropically from 100 meter per second to 300 meter per second in a nozzle, right? And here they are asking if the temperature at the inlet of the nozzle is 127 degrees centigrade, the inlet Mach number will be what? So, so there is a nozzle. Now the shape of the nozzle, again, if that is a compressible flow, so shape of the nozzle will not be always be converging, right? That depending on the Mach number, what we are taking. This is the inlet section I'm assuming, and this is the outlet section. Inlet section 1, outlet section 2. At the inlet section, they are saying what is the value of Mach number. They are asking Mach number at point 1, and Mach number at point 2. They are not asking. They are asking inlet Mach number. Now it has been accelerated from V1, that is 100 meter per second, to V2, that is 300 meter per second. The next thing we have to calculate what is the Mach number inlet. Mach number at the inlet will be velocity at the inlet, velocity of the flow at the inlet to the speed of sound. What is the speed of sound? We know that the speed of sound will be dp by d rho at uh, whatever the isentropically, whatever the value of dp by dp rho is there, that is the value of c. We can also write c as gamma rd. We can also write c as gamma rt. Now note down the next thing. How to calculate c? C will be equal to under root of gamma. Gamma is what? 1.4. Gamma is basically specific heat ratio. For the air, it will be 1.4. That is for diatomic gases, it will be 1.4. 1.4 into 287, that is the value of R. That is the value of R into T. What is the temperature at the inlet they have given? 127 plus 273 Kelvin. So when you calculate from here, 127 plus 273, you will be getting 400 Kelvin. Now when you calculate 1.4 into 287 into 400, and when you take under root of that, you will be getting 400.898 meter per second. Then what is the Mach number at the inlet section? Mach number at the inlet section will be V1. What is the value of V1? 100 meter per second. And what is the value of C? That is 400.898. So overall, when you calculate the Mach number at the inlet, you will be getting 0.25. Means exact value, if you ask me, 0.249. That is approximate to 0.25. So A will be correct. A will be correct. That is the inlet Mach number. That is what we are getting, the inlet Mach number. Now here we got the answer. That is okay. But we have to see some other aspect of this particular question. What is the Mach number at the exit? What is the Mach number at the exit? See here, V1 divided by C1. That is the Mach number for the inlet section. That is the Mach number for the inlet section. Now here, when you see from area ratio formula, dA by A, that is equal to dV by B, Mach number is square minus 1. At the inlet, Mach number is what? Less than 1. When it is less than 1, that means what? It is subsonic flow. Mach number is, we are getting even below than zero point 0.3, right? So we can assume that this particular flow to be incompressible flow. When it is less than zero point 0.3, then we can assume this flow to be incompressible flow. Mach number at the inlet is less than 1. That means this particular quantity is what? Negative. Area is what? Increasing or decreasing? Area is also decreasing, as we have shown like this here. So what about the velocity? dV by V should be positive, and that is what happening, my dear friend. See that velocity at the outlet section is what? 300 meter per second. It has been increased from 100 to 300, right? That is what we call this to be subsonic nozzle. Note down. This is what we have area ratio formula. Area velocity relation. Area velocity relation. What is the next segment? The next segment will be the next question. Question number 56. A manometer is used to measure the pressure of a gas in a tank. The fluid which is used to measure this particular pressure has a specific gravity of 0.85. The manometer column height is 55 centimeter as shown in the figure. If the local atmospheric pressure, if the local atmospheric pressure which is acting, that is 96 kilopascal, what is the absolute pressure in the tank? What is the absolute pressure? Absolute pressure in the tank, they are asking. So to solve this problem, I'm taking the tank first of all, and through this tank there is a manometer which is being connected, and this manometer we have from here to here some other liquid that we call manometric fluid, that we call manometric fluid, and here we are subjecting this top manometric fluid to atmospheric pressure with the 96 kilopascal, and the height from here to here they have given 55 centimeter. Now you assume two level. This is the point A, this is the point B. Pressure at point A will be equal to pressure at point B according to manometric equation. Pressure at point A will be pressure which are there in the tank only. Pressure which are there in the tank only. Pressure at point A will be exactly equal to pressure in the tank, because there is a no height of the liquid here. There is a no height of the such a liquid. No height is given. That means we can assume it has been connected at the same point. Now What about pressure at the point B? Pressure at the point B will be the manometric fluid, which is exerting the pressure, rho m into g into height. Now we have to calculate absolute pressure. Absolute pressure, everyone know that, atmospheric pressure plus gauge pressure. This particular thing is nothing but your gauge pressure. Then if we want to calculate absolute pressure, then we have to add atmospheric pressure. There is a no doubt. Now, what is the manometric fluid specific gravity? What is the manometric fluid specific gravity? Specific gravity is zero point 0.5. What is the meaning of specific gravity? Rho of any fluid to rho of standard fluid. What is the in case of liquid? What is the standard fluid we are assuming? We are assuming the standard fluid to be density of water at 4 degrees centigrade, right? So here 0.85 into 1000, that will give me density of manometric fluid. That I am writing over here 850. G value is 9.8. Height is what? 0.55 meter. This plus 96 kilopascal. If I convert this into kilopascal, I need to divide by 1000. So now when you do the calculation, 850 into 9.81 into 0.55 divided by 1000 plus 96, you will be getting 100.586 kilopascal. That is the value of pressure in the tank, which is approximate to 100.6 kilopascal. 100.6 kilopascal. C. Which option is correct? C option is correct. Note down. 100.6. If they would have been asking the pressure in the tank, that gauge pressure only, then the answer would have been 100 minus this 96. The answer must be 4.6 kilopascal approximately. If they would have been asking the gauge pressure in the tank, the answer must be 4.6. But right now they are asking the tank pressure, that to absolute. Then what is the absolute pressure we have? Absolute pressure will be this one. Then we need to add atmospheric pressure plus gauge pressure. Because if this is a zero level and if this is the atmospheric pressure, above this one, whatever the pressure is there, that is a gauge pressure we call. Then from here to here, total pressure, we call this to be absolute pressure. Absolute pressure. Right? Now, in this question, a crane is used to lower the weight. Crane is a machine basically which is used to lower the weight or lift the weight. Here, in case of this, they are lowering the weight into the sea. That sea is having some density of 1025 kilogram per meter cube for an underwater constructions. What is the percentage reduction in the tension in the rope of the crane due to the rectangular concrete block when it is completely immersed in the water as compared to tension in the rope when we have suspended in the air? That means if they are asking this particular problem, if I say here a crane, this is the concrete block of whatever the dimension of whatever the volume, let's say V. It has been suspended in the air. It has been suspended in the air. It has been suspended in the air. Tension in the rope will be T, and mg of concrete will be acting in these downward directions. Whatever the tension will be there, I'm calling this tension to be T1. Whatever the tension will be there in the rope, I'm calling this tension to be uh, T1. tension in the rope when it is being suspended in the air. When it is suspended in air, what is the see now if it is suspended in the air, of course there will be some buoyancy force by air, but that buoyancy force, because you know that what is the buoyancy force will be rho of the any fluid g into volume of that concrete block. But here rho of fluid is such a low value as compared to weight of the concrete plot or density of the concrete block, that we are neglecting here the buoyancy force. What we are doing, we are neglecting. So T1 can be written as rho g v, rho of concrete block. Rho of concrete block is given as 2300 kilogram per meter cube. And what is the density of fluid or liquid is 1025 kilogram meter cube. Now when you calculate here T1, rho of concrete will be 2300 Z into V. On the other hand, when we suspend this particular concrete block inside the liquid, again tension in the rho will be T2 now, the weight of the concrete block here. And because now this is being replacing the fluid which is heavier somewhat as compared to air, so this will be applying some kind of buoyancy force. It will be applying some kind of buoyancy force from centroid of this displaced fluid, from the centroid of this particular displaced fluid, like this. Now this buoyancy force, now if we do balancing the force, T2 will be equal to what? T2 plus FB of water mg. T2 will be what? Rho of concrete G into V minus of buoyancy force. Buoyancy force I told you. Rho of fluid G into volume of concrete. So T2 can be written as 2300 minus 1025 Z into V. That is my T2 value. And this is my T1 value. They are asking what is the percentage reduction will be happening in the tension of what? Tension of rope. So we are asked to find T1 minus T2 by T1 into 100. That is percentage reduction in the rope tension. So T1 minus T2 by T1. T1 is what? 2300. If you calculate T2, you will be getting 2300 minus 1025. So you will be getting 1275 G into V. So now put that value, 2300 minus 1275 divided by 2300 into 1000. So what you will be getting 2300 minus 1275 divided by 2300. So now when you calculate, you will be getting 44.6 percentage. That much of reduction will happen. So which option is correct? The option A will be correct. Approximate, it is nearer to what? 45 percentage. 45 percentage. Make a note of it. Remember the free body diagram here, like this. Buoyancy force will be acting. What is the position? What is the point through which the buoyancy force will be acting? The buoyancy force is acting always at the centroid of displaced fluid. Here, the displaced fluid and the volume which is being uh, surrounded by the block will be same, because both has been they have given that block, a concrete block has been submerged completely. Not, it is not like a floating condition. It is being submerged completely. Read the problem. It is being submerged, immersed completely. So both the points, that is weight point as well as the buoyancy force point, will be exactly the same, P point. Similarly, my different, when we talk about the here, what we call the buoyancy force because of the air, that must be acting at the centroid here. that also must be acting at the centroid of displace, because again it is like a completely submerged in a air media, right? But here we are neglecting because density of the air is almost like a 1 kilogram per meter cube, so that you can neglect. Even though if you want to include, you better include that, and you calculate, hardly you will get any changes. Again, we cannot assume anything regarding here density of the air, because that they have not given in the problem. But when you read the data book, when you read the air data book, then you will find density of the air is not more than 1.2 or 1.3 kilogram per meter cube. That's a very very low as compared to 2300. Right. Moving on to the next question. The next question they are asking: study incompressible, study incompressible two-dimensional velocity field. Two-dimensional means here they have given u component and v component. That definitely it is gonna be 2D flow field. Here whether it is a incompressible or not, let's check it. Let's check it. So for incompressible, 2D incompressible, for 2D incompressible flow, for 2D incompressible flow, we know that general continuity equation. In that, when we simplify for 2D incompressible flow, then we can write dou u by dou x plus dou v by dou y equal to 0. I'm not writing a complete general continuity equation because it is not required for this question. I'm just testing whether this question data has been given correctly or not. That's it. What is the u component? U component is nothing but zero point 0.5 plus 0.8 x, and v component is 1.5 minus 0.8 y. Dou u by dou x will be zero point 0.8 plus dou v by dou y will be minus 0.8. That will give me 0. That is 0 means it is satisfying 2D incompressible flow field. No doubt about it. What is the meaning of stagnation point? At a particular stagnation point, let's say flow is happening over this curved surface. At the particular point, let's say at particular point P, here P, suddenly the velocity will become zero. The moment it is striking the nose of the, let's say this aeroplane, what will happen? Suddenly it becoming what? Zero. At the point P, at point P, what is happening, my dear friend? Total velocity vector is zero. That means we can write 0 I cap plus 0 j cap, right? That means u component will be 0, v component has to be 0. That means zero point 0.5 plus zero point 0.8 x, that is 0. X will be what? X will be zero point 0.5 divided by zero point 0.8, that is minus 0.625. And what is the y value? Y value will be 1.5 minus zero point 0.8 y, that is 0. Then y will be 1.875. That means you are getting one coordinate in a 2D flow field at a coordinates of minus 0.625 and 1.875. You are getting zero velocity. How many stagnation point? One. Only one coordinates you have, right? That means somewhere here, where we have allocated the point, there might be some origin. Origin might be like this, where uh, the point P distance is what? Minus 0.625 and plus what we call 1.875. Only one stagnation point we are getting. If this would have been zero point 0.5 plus zero point 0.8, let's say here 0.5 minus zero point 0.8 x square, then x value might be 2 under root of, when you take under root, plus minus you will get. In that case, you might be getting more than one stagnation point. But here only one coordinates xy, that's it. See, if you have only xy, you can allocate only one point, right, in a 2D flow field. X comma y, that's it. So only one is stagnation point, P. C is correct, right? So remember, regarding fluid mechanics and hydraulic machine, ISRO is so much fascinated or maybe so much inspired by Sinjal textbook, Sinjal and Simbala. They have given probably 2007 onwards till 2022, they have given the questions directly from Sinjal. No other textbook they have followed. Directly they copy pasted each and every, even a salt example, they have copy pasted and kept in the paper. Fluid mechanics and hydraulic machine, blindly you can follow Sinjal and Simbala textbook. I'm not just telling you as a random guess or basically what no, I'm not hyping anything about the Sinjal textbook. You can check every question you will find in Sinjal and Simbala textbook. Even this question also. Now, right now you will say, sir, I know this question, but at that particular point, many students were not aware of this such a question. Right. So Sinjal and Simbala, you please note down. Sinjal and Simbala, both for hydraulic machine and both for the fluid mechanics. You please follow that book. Follow that book means whatever you have in your notes already, right? That you know that. But apart from that, you try to match. You read the chapter, second chapter, third chapter, whether you have something that you have not written, you please note down from the textbook or so from the salt example. That will be asked in what we call in ISRO paper, right? Again, do not waste the time, sir. Whether you are saying correctly or not, whether they have taken the question from the book or not. If you want to waste the time, again you can waste the time simply one day by checking, and you will find that they have taken the questions from that particular book, right? If I have done the basically research, then why you will do that? You simply try to stick to that book and try to follow and save the time, right? Okay. Try to see the next question. A piezometer and the pitot tube are tapped in a horizontal water pipe as shown in the figure. The velocity of the water at the center of the pipe will be how much? Read the problem first of all. Note on the particular whatever the diagram they have given, and then we will proceed. The piezometer and the pitot tube are tapped in a horizontal water pipe as shown in the figure. The velocity of the water at the center of the pipe. They are asking what is a V1. What is this from here to here? Static head. What is this? Because see, whatever the height of the liquid is there till this point, that is already given by this piezometer. Piezometer is a static pressure measurement device, right? That cannot measure any stagnation pressure. No doubt. Measures static pressure. Measures stagnation pressure. What is this dynamic head? How much of dynamic head is given? I think they have not shown here. This is 12 centimeter. Apply the Bernoulli equation between 1 and 2. Just apply the Bernoulli equation between 1 and 2. Just to apply the Bernoulli equation between 1 and 2. Apply Bernoulli equation between 1 and 2. You will be getting P1 by rho g plus V1 square by 2g plus Z1. Z1 and Z2 will be same because they are both the points, point number one, and point number two. Point number two, it is just at the inlet of pitot tube. Pitot tube like this. just at the inlet of theta tube. That means the velocity at the point 2 will become what? 0. Just at the inlet of theta tube. Just at the inlet of theta tube. That means just like a stagnation point. Stagnation point, I told you velocity has to be 0. Right? What is the P1 by rho g? That is a static pressure head. What is the P2 by rho g? That is a stagnation. Stagnation pressure head. What is the stagnation pressure head? Stagnation pressure head will be static plus dynamic. The total height from here to here. What is the stagnation pressure head value? Value will be 12 plus 10. That is 22 centimeter. 22 centimeter. 12 plus 10. 22 centimeter. That is the stagnation pressure head. Stagnation pressure head. Now V1 square by 2g. This we calling stagnation pressure head. What? P2 by rho g. P2 by rho g I am calling P2 by rho g. That is H stagnation. And this I am calling H static minus H static. So when you calculate V1, that is under root of 2gh dynamic. Because stagnation minus static will give you H dynamic, right? H dynamic. Now when you calculate V1, 2 into 9.81 H dynamic. H dynamic is what? 0.12 meter. Now when you calculate 2 into 9.81 into 0.12, under root of 2.3544. Now when you take under root of that, you will be getting 1.53 meter per second. Which option is correct? B is correct. Again, I'm not saying you to calculate by calculator. You can guess very easily. How you can guess very easily? You can guess very easily because 2.34, right? 2.25, we know under root of that 1.5. It is just more than that. So 1.53 will be correct. Understanding? So all of you understood this particular problem? If you can reply by yes and no. Yes. Okay. Try to see this question. Again, a very simple problem from this here. Surface tension they have asked. What they are asking? They are asking the pressure difference between inside and outside of a liquid droplet of diameter d due to surface tension. Droplet formation. When the droplet formation will be taking place, then when you take any droplet, let's say this is a droplet which we have drawn. This liquid droplet, that means in this droplet we have the liquid which is having a pressure, let's say PT, and outside we have the pressure PATM, for example. Let's say, for example, they have PATM. Now, this PT will be more than PATM. Then it will try to burst this liquid droplet. The difference of these two we are calling delta P. Delta P. PET is nothing but total pressure, right? And how to calculate that? How to calculate that? For that, we need to make free body diagram like this. Or we can make liquid half part I am drawing, where from this it will be subjected to surface tension, and this liquid droplet will be subjected to the pressure. How much? Delta P. Delta P. So now bursting force, this pressure force will be equal to surface tension force. Surface tension. Bursting force will be delta P into pi by 4 d square. Surface tension is acting along the circumference. That is sigma into sigma is what? Newton per meter. We have to multiply with the parameter pi d. And that's how you will get delta P, that is 4 sigma divided by 4 sigma divided by d, my dear friend. Make a note of it. This liquid droplet, it consists of single liquid inside that particular droplet. So what should be the answer? A option should be correct. What will happen when I consist of two liquid droplet? Let's say, for example, here we have example number 2. Double droplet, where just like a soap bubble. So here I'm considering, let's say for helium, here we have a liquid, and outside we have air. Now if I'll be asking you how much of delta P, that pressure which is exerted, what you will say? Delta P will be 4 sigma I divided by di plus 4 sigma naught divided by d naught, whereas sigma I will be surface tension due to liquid helium interface. The liquid and helium both are uh, making one interface. You can see by green color here, right? Liquid helium interface, and whatever the sigma naught is there, what we are writing sigma naught is there because of the liquid air interface. See here, this one black color, right? This is a two interface problem. In earlier particular problem, we have only one interface. See that this red color which I'm marking, this was only one interface. Here we have air, here we have the liquid. That's why single value is coming, right? Now what is happening with the soap bubble? What will be happening with the soap bubble? What will be happening with the soap bubble? Again there will be two interface. Again there will be two interface. Tulsi, see that. Example number 3, soap droplet, soap bubble. In case of soap bubble, what is happening? In case of soap bubble, what is happening? See that here. Here we have air. Here we have the liquid. Again we have air. This is example of soap bubble. In this soap bubble, what is happening? Again use the same formula. What the formula we have used here? Now here we have used this as internal diameter and this as outer diameter. For soap bubble, instead of helium, we have again air. So again, it's look like a two interface problem. It's look like a two interface problem where we can write delta P as 4 sigma divided by di plus 4 sigma divided by d naught. Why we are writing sigma sigma naught, sigma I sigma naught? Because air liquid, and again liquid air. They are like a same thing. Sigma I equal to sigma naught equal to sigma only. But here you might be thinking, sir, the formula for the soap bubble they used to write 8 sigma by d. The formula for delta p they used to write 8 sigma by d, but not like with the formula which you have written. If you directly remember like this, that is a big blunder. See, of course, whatever the diameter we are assuming, that is almost like a same diameter. Inner diameter and outer diameter, they don't have any difference. Even slight difference will be there that we are neglecting. So that we can write 4 sigma by d, plus 4 sigma by d, that will become 8 sigma by d. Understanding my point? Right. In earlier case, we got the helium here. The liquid, whatever he is there, I have placed instead of air, I have placed helium. You know that helium and liquid and air, both have different surface tension. Right? Surface tension is a liquid property. The force they exert on a surface per unit length, right? And definitely, whatever the two liquids are there, they must be immiscible. Even though we talk about, let's say, the air bubble is there, which is there inside the liquid. For example, if I place, for example, this is a air bubble. Let's say, for example, we have air. Here we have the liquid. I'm talking about example number 4. I'm talking about example number 4. Here we have the liquid. Again, we have this is a liquid 1, and outside it is being subjected to another liquid number 2, and this bubble is there at a height of, let's say, small h. Again, what will be delta p in this case? Then delta p in this case will be, can be written as p minus p atm. That is equal to, don't think that do not think that here we will have what we call, or let's say if I placed in the same liquid. Now, the moment if I place this droplet inside the particular river or anything, like what will happen? Only one interface will be there. This air bubble is there, that will be filled with the, again, liquid. So there is only one interface. So we can write rho gh plus 4 sigma by d. Make a note of it. This is the pressure because of the hydrostatic, plus this will be the pressure because of surface tension that will be acting. Because when you place this particular double droplet inside that what we call liquid, the liquid will fill. The liquid will be filled in that droplet, and that complete this interface will be gone. The green interface which you are looking right now, this will be gone, and that will look like this. Uh, Only single interface. Or whatever we can say here, what we can say, we can understand in other manner also. Initially we got to know there was a air and air. This is the air, this is what we got, the liquid. Again we got the air. So here we got the two particular interface: air liquid, liquid air, for example, right? Air liquid, liquid air, for example. Now second segment, when I place inside the liquid, what will be happening, this air will be there, this particular air will be there, this particular air, whatever is there, that will be there. But this black color interface, which I am denoting by blue color here, that will be gone, because now this liquid and this liquid, they are what, mixable with each other. They are not immiscible, they are miscible with each other. So that will make only single interface. That's why not 8 sigma by d, it will be 4 sigma by d, right? Even you place a helium or whatever we call air, let's say, for to give more sort of explanation, let me place it here, helium. Helium. So now helium will be there, but this particular liquid and this liquid, they are mixable with each other. Whenever they are mixable, no surface tension will be produced. For a liquid-liquid combination, both the liquids should be immiscible with each other, right? So here only sigma is there because of liquid helium interface. That's it. So surface tension is all about the interface, not about the uh, what you might have understood. Note on this particular problem. Stream function, which is being defined by like this, the resultant velocity. First of all, we will try to go through understanding of stream functions, right? Stream functions. What is the meaning of stream functions? Note of the problem and try to solve it. Note on stream function. Stream functions are the flow towards the horizontal to the surface. What it means? If you want to explore, you can explore more. Stream functions are the flow towards the horizontal to the surface. It's look like a little bit not correct. No doubt, it is defined as a scalar function of. First of all, it is a scalar function. It is defined as a scalar function of space and time, such that such that for an incompressible flow, for an incompressible flow, it doesn't mean, my statement doesn't mean that it is not defined for a compressible flow. We have a stream function for compressible flow also, but for this moment, I'm just telling you for incompressible flow, right? It is defined as a scalar function of space and time, such that for an incompressible flow, the partial differentiation partial differentiation of stream function, we denoted by psi like this. Partial differentiation of psi with respect to any directions. With respect to any direction, with respect to any direction, gives the velocity vector, gives the velocity vector normal to that directions. Normal to that direction. Which direction? This direction, this direction. That means if you take x and y, and first of all, it is valid only for 2D flow. It is only valid for 2D flow, not for the 3D flow. Whenever you differentiate psi with respect to x, it will give you velocity which are perpendicular to the x. Which velocity is perpendicular to x? This is u, this is v. V is perpendicular, so it will give you velocity v. Similarly, when you differentiate psi with respect to y, it will give you the velocity. It will give you the velocity perpendicular to the y direction. What is the velocity? What is the velocity perpendicular to the y direction? U. But here we are adding minus sign. Here we are adding plus sign. No doubt. So what is the u? U is nothing but dou psi by dou y. And what is the psi in the particular problem? When you see the problem, 4x minus 3y. 4x minus 3y. So that will be, u will be equal to minus 3, and v will be dou psi by dou psi by uh, dou x, minus of dou psi by dou x. So that will be minus of 4. So that will be minus 4. They are asking what is the velocity, what is the resultant velocity at any point. You got u, you got v. Resultant will be what? Somewhere here. That is the resultant velocity component. So that resultant velocity component will be under root of u square plus u square. So that will be minus 3 square plus minus 4 square. That will give you 5 unit per second. Which answer is correct? So 5 is not given in the option. No, 5 is correct. Here you can replace, I think data might not be correct. Here 5 and D will be correct. 5 unit per second will be correct answer for this. Five unit per second will be correct answer for this question. Understanding, Tulsi? Now 61, we got the answer for this. That is, this will be the answer. Note on the next question. We'll try to go through the next question. The next particular question is coefficient of discharge for an orifice meter will be coefficient of discharge for an orifice. Generally, the coefficient of discharge for an orifice meter will be very very low, in the range of 0.60, 0.6 to 0.64. Why? When you see venturimeter having the CD value in the range of something like a 0.94 to 0.98. Why there is a difference of these two values? Why such a high value difference is there between these two? And CD for flow nozzle also. 0.7 to 0.74. Now you understood that the value, right? Now why, when you see the venturi meter, there was a smooth transition like this, right? There was a smooth transition which happened between converging section as well as throat section, then diverging section. There was a very smooth transition. See that? That's why the losses are very very in a limiting value. Whereas when you compare orifice meter, when you see the orifice meter, there is a section called here. Just a moment. I draw orifice meter for you. The very rough diagram I'm making, not exactly to the same scale. Here, when you see the orifice meter, just like this, we have a segment where it has been connected to wall. Again, we have connected here. Now, try understanding here when you see the diagram, right? The side view of that, here the flow is happening. That's look like this, and then we have a plate. We have a plate, and then we have a hole there, like this. Through this hole, they are going. The liquid is going, passing. Right. So suddenly we make the hole so that the liquid is going to be passed like this, or we can say that here, uh, this particular arrangement, what we can make. There are different types of orifice meters. So if I make the arrangement, look, if I take example of some other here, if I make this is the hole. Through this, the liquid is flowing. When the liquid will flow, then what will happen? There will be very 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 minimum vena contractor area will be developed. Then it is going to expand like this. So there is a sudden contraction is happening because of the sharp edges, right? There will be sudden contraction will happen. This is the hole through which the liquid is flowing. And now I have connected here with the flange and bolt section like this. Means the nut and bolt are there in throughout the circumference, right? Here, right? Now here what we are following here, there is a sudden contraction will happen. But in case of what you have understood, in case of you have understood very clearly, in case of venturi meter, there was a smooth transition. But here there's a not so smooth transition there because there is a sharp edges. See that point P and point Q, and because of that, the vena contractor will happen somewhere here. The flow will stabilize here, right? That's the reason we place what we call manometer, differential U2 manometer in between these two segments like this. Nice. Because we want to stabilize the streamline that is being parallel with each other, something like this. Now because of this P and Q point, there is a sharp edges. Because of that only, there is a lot of losses will happen in the discharge. That's the reason Q actual will be much much less than Q theoretical, because Q actual We know that is CD times of Q theoretical. QD theoretical. CD into Q theoretical. CD value is very, very low. That's the reason Q actually is very also got reduced. Right? Understanding my point? That is what the practical observations. When you do the theoretical observations, theoretical derivations, you will find that venturimeter CD value will be somewhat higher than CD value for orifice meter. Not somewhat higher. CD value for venturimeter is much higher than orifice meter. Right. So a lot of losses will happen. Losses are very, very high in case of orifice meter. This is what we have drawn orifice meter. Right. This is what we have flange section. The flange section is being fitted to the pipe. Right. We use frequently this particular instrument in chemical industries. Whenever we have any leakage in the pipes, we place it and we find the discharge. How much of leakage is happening, right? No. Try to solve the 63rd one. What will be the hydraulic diameter for a rectangular duct? For a rectangular duct, they are asking what is the hydraulic diameter. This is A, this is B. This will be the length. Now, hydraulic diameter, you know the formula. We sometimes also say characteristic length 4 into cross sectional area by weighted parameter. Now, they have not given whether this particular rectangular duct is half filled or full filled. Now, this particular rectangular duct is what? Fully filled with the liquid. It has been assumed that the liquid is touching all the surfaces or sides of this particular rectangular duct. It has been fully occupied. Even top surface also it is touching. So what is the weighted parameter? The weighted parameter will be all the sides when we have to account. That means 2 times of A into A plus B. So hydraulic diameter will be 4 into A into B, 2 times of A plus B. So which option is correct? D will be correct. B will be correct. A very similar example they ask one more time in ISRO, but what they have done, they have changed the pattern of the question. The hydraulic diameter of a rectangular duct, which is being half filled, they have given, means the top surface is not being touched. That means it is only touching here like this. They have given like this. They are saying it is being only half filled. That means it is half filled up to this point. That means it is not touching whatever the point you are observing. The top surface it has not been touching. Only it is wetting A sides, B sides, and this B sides. In that particular case, my different hydraulic diameter will be what? If I take example number 2, hydraulic diameter will be 4 into cross-sectional area by weighted parameter. Now weighted parameter not be A plus B plus B. Earlier we got like this. But now this particular surface, it is not being touched. So what we can write? Weighted parameter will be 2B plus A. This will be the hydraulic diameter. So this denominator, that is a weighted parameter, that word is very, very important. Not only parameter, weighted parameter, that means the sites which is being touched by this liquid water. Okay, moving on to the next particular problem. Multi-stage centrifugal pumps. Multi-stage centrifugal pump. Now, whenever we talk about the pump, basically a single pump sometimes may not be sufficient to increase the pressure. So generally, we employed pump in series, or basically pumps in parallel combinations. Whenever the pumps we employ in basically in series combination, whenever we employ pumps that too in series combinations, then what we'll be doing? Basically, we are increasing whatever the head will be increased. If head will be increased, automatically pressure will be increased. Head will be increasing, and that will lead to increase the pressure. Whereas pump in case of parallel combination will give you discharge higher than single pump discharge. The multi-stage centrifugal pumps are basically practically purposes we use only for increasing the high pressure, not to increase the discharge. For increasing the discharge, we select some suitable pump types of pump, right? In case of course, we have centrifugal pump, which is automatically giving you the high pressure, a high particular value of discharge, but it is giving you the low pressure ratio as compared to a reciprocating pump. Now, to increase the pressure, definitely we have to use pump in series combinations. And that's where we involve the concept of multi-stages. Multi-stage, it can be two-way. Remember, it can be two-way. One is a series way, other is a parallel way. But again, they are somewhat practical questions, right? Otherwise, you might be taking the option called B, but B is not suitable with respect to practical point of view when you talk about centrifugal pump. Again, for that, you need to read completely pump chapter. What is the operating characteristic curve and all those things. In this particular lecture, I cannot complete because I need separate 1 hour or 1 hour 30 minutes for discussing the characteristic curve of a particular pump and why we involve the multi-stage centrifugal pump only for increasing the pressure. Okay, so that's we have talked about the concept of multi-stage centrifugal pump. The next question is match the following question. They have given regarding the hydraulic machines, hydraulic turbines. Hydraulic turbine, basically, when we see any hydraulic turbine, we have invert flow reaction turbine or tangential flow turbines. Right? We have different types of turbine based on the direction of flow of fluid. Based on the direction of flow of fluid, we can classify the different types of turbine. Right? Now, here we can classify impulse turbine, note down, impulse turbine, purely on the basis of forces that gonna produced. Impulse turbine, we also call Pelton turbine. We also call tangential flow turbine. Tangential flow turbine. Tangential flow turbine. Impulse turbine, Pelton turbine, tangential flow turbine. That is the meaning of this. Now, second types of turbine we have impulse reaction turbine. What is that? Impulse reaction turbine. Impulse reaction turbine. Now, impulse reaction turbine. What are all the again in this one? What are all the turbines will be coming? Tulsi, can you please name that? What are all the types of impulse reaction turbine? Can you say Francis turbine? If I say a Francis turbine, then in which category it will be coming? Whether it is coming tangentially or radially. See, what is the meaning of tangentially and radially? You have suppose blade like this. For example, you have the blades. I've drawn only the runner blades, not the fixed vanes. Whenever the flow will be happening tangentially, when the flow is happening like this, that is a radial flow, radially inward flow. Usually these things will happen in case of turbine, hydraulic turbine. Tangential flow means it will be flowing tangentially. It will be flowing tangentially. Let's say we have the turbine, we have a tangential flow like this. This particular flow is nothing but tangential flow. Sometime, sometime we say axial flow turbine. Axial flow means parallel to the shaft. Let's say this is a shaft. Sometimes the flow will happen like this, parallel to this. Means assume that the flow is happening perpendicular to the plane of laptop board, right? So that laptop, what we call perpendicular to the screen which you are looking right now. So perpendicular to this will be axial flow. So based on the direction of flow, we have three type category: radial flow, tangential flow, axial flow. Now tell me impulse reaction turbine. We also call this to be radial flow. Under which under this particular category, which kind of turbine will be mostly suited? Here we have Francis turbine. Francis turbine. A third category we have axial flow turbine. Axial flow reaction turbine. Flow will be happening parallel to the shaft. Shaft. Axial flow reaction turbine. So we have Kaplan turbine. Now when you match the following option, Kaplan turbine, we have inward flow reaction turbine. Parson turbine is a Parson is basically 50% degree reaction turbine. We also call 50% degree of reaction turbine. That will be steam turbine. Francis turbine, we know that again we have, sorry, this, no, 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 this. Here Kaplan turbine, inward flow reaction turbine. Francis turbine will be again inward flow reaction turbine. See here. And Parson reaction turbine will be this one. So P will be for one, P will be for one. Only we have two options. Then K will be for two, and here Francis turbine will be two. So C option seems to be correct here, where you are saying that Kaplan and Francis both are inward flow reaction turbine, right? But the flow will be different. One is a radial flow, other is a axial flow. In case of Kaplan also, up to some part it will be radial flow, but after some time, after radial flow, it will be axial flow, right? So now, but there is a different types of turbine what we are observing. First time you might be thinking, sir, pump is categorizing under outward flow. Pump is categorized under outward flow. What we call centrifugal pump, centrifugal pump, radial outward flow, radial outward flow. Machines. Now you might be thinking, so this foreign on whatever the foreign on this particular turbine is there, how this can be something like a turbine? But yes, it has been developed in 8027. We don't use nowadays, right? And this we call outward flow reaction turbine. So F naught will be 3. So definitely C option is correct. Again, no need to have the perfect idea about the third option, because based on 1, 2, and 4, you are taking the option, right? So note down. right? So that is the most, see, some of you might be thinking, sir, water should be coming, it has to impel, it has to give its water energy, then only the mechanical energy will be there. But how in case of outward flow reaction, how by the outward flow the power can be produced? And that's what is a very very surprising thing. Like, how and why I'm not discussing here, because that is being used before Francis turbine has been developed. So recently and nowadays we are using that Francis turbine. So I'm not going for past development or history of the turbine where we have been using this earlier than the Francis turbine. Right? Because no need of that, because in any interview they will not be asking that particular turbine. But of course, if you are very much interested, you please go through the working animation or principle of this particular turbine, because how the outflow flow will produce this up power, that's a very surprising thing. Because whenever the outflow flow will be there, we we will be giving the water energy rather than getting the mechanical energy. That is what happening in centrifugal pump. What I want to say, inward opposite outward, right? Inward opposite outward. In case of pump we are giving the power input, in case of turbine we are getting the power output. Surprisingly, how this turbine is getting the power output without giving the power input, that's a big question mark. If you want to have curiosity about the fundamental of all those things, mechanisms, you please go through that. Now, the next particular question will be 73rd. Which of the following pressure gauge is generally used for calibration of other pressure measuring instrument? See, you might have seen the barometer, you might have seen the piezometer, you might have seen the manometer, but what is this new thing? It is not a very new thing, because whatever the Borden tube pressure gauge and diaphragm pressure gauge and deadweight pressure gauge already there in the Sinjar and Simbala. In fact, in their ISRO interview also, they are asking this question. Explain the working of Borden tube. What is the accuracy of Borden tube? How we do the calibration of Borden tube? All these things are questions in ISRO interview. So definitely you should not avoid those questions, and you have to read not directly by hearting from any sources or any other thing that the right answer is C or what. Of course, C is the right answer. Nobody can deny from the fact, but why that answer is correct and why not other answers, and what is the working principle of other instrument? Because barometer, you know that, piezometer also you know, right? The next thing we will discuss, this Borden tube pressure gauge. Note down first. Here, which is 73rd question. Borden tube pressure gauge. Most commonly very cost effective, very very low cost. In most of the industry, we follow this. Whenever you go to any pipeline industry, right, you will find this particular Borden tube. Directly you cannot see, because if there is a pipe, to this pipe there is a pressure gauge. But exactly, and there is a dial indicator where the numbers are being indicated. But generally you won't find directly in the case of by observing with our own eyes, you have to see very carefully. Burden tubes are very, very different types based on the shape and size. We can classify again burden tubes in different categories. One will be category of C type, other is a category of what we call spiral shape, right? So here, let's for example, we are drawing for the C type, and through this one, I'm drawing not exact instrument. I'm just drawing the approximate. I'm not drawing all the parts of that. This is nothing but dial indicator. Now here, let's say the fluid is coming. Whatever the fluid pressure is, right? There is a pipeline, right? And the fluid is going in this pipeline. Now the fluid pressure we want to measure. Generally, it is working on the principle of before fluid is getting passed in the tube, this will be set at an indicator of 0. But generally, when the fluid is passing into this tube, this particular tube, bent tube, what will happen? This particular fluid will be, this particular tube will be stretched. When the fluid, this particular tube will be stretched, what will happen? After stretching this particular tube, this needle will be deflected. This particular needle will be deflected on the dial indicator. Of course, that will not be deflected in the air, right? It will have some instrument like it will be connected with the pinion gear mechanisms. I have not drawn. I told you this is a very very rough diagram, right? Now here, when the liquid is passing in this particular tube, the tube will be getting deflected. The tube will be getting stretched. Because of that, the needle which is got connected. See, when the tube is getting deflected like this or like this, the needle which is being connected, that will also be moving like this or like this. That's how the reading will be there. That reading will be based on the fluid pressure. The whatever the reading is there, it will be directly proportional to the pressure of the fluids. Pressure of the fluid, and that's what we can measure by using the value. That is the working principle of Bourdon tube pressure gauge. Now when you compare this with the diaphragm, the second type, diaphragm pressure gauge, the diaphragm pressure gauge, what you are understanding from the diaphragm pressure gauge here? Here you can note down the diaphragm pressure gauge, something like this. Again this is the pinion. Please understand, this is the pinion. It is connected with the pinion and gear mechanisms. Pinion and gear mechanisms. This is what we call sector, and the fluid is being passing. This is nothing but what we call diaphragm pressure gauge. It's a very simple principle. The diaphragm is basically a material of certain diameter d, where when the fluid is passing and just applying the forces on this diaphragm is a material which will be getting deflected. When it will be getting deflected, whatever the this particular needle which is being connected through this diaphragm and sector, it will be deflected. When this will be deflected, the pinion will be start rotating. The pinion will be start rotating. When the pinion will be start rotating, the indicator will also be start moving. That's a simple arrangement of diaphragm pressure gauge, right? But these are the simple instrument. But whether this instrument, when you continuously, because you know that this instrument we are not using for one time, right? Every time in industry we used to use this instrument multiple times. There might be some wear and tear. There might be some corrosion might be happening in the pipe or maybe in the tube. So whether reading which is given by this particular burden tube and this diaphragm pressure gauge correct or not, we have to do calibrations, right? For calibration, what we use dead weight pressure gauge. They are highly precise, high accurate pressure gauge, which is used to compare for measuring the other instrument values or accuracies. So note down first of all what is the meaning of calibration, because this word will be coming frequently, and this has been asked In most of the interview, whether you go any DRD or ISRO, they will be asking you the calibration. Either they will be asking you how you do the calibration of what we call 1 year caliper or micrometer. Then what you will answer, right? So please note down. The process involves obtaining a reading. The process involves obtaining a reading from the instrument and measuring its variation in reading obtained from obtained from standard instrument. In short, if you want to measure the accuracy of burden tube or diaphragm pressure gauge, we have to use dead weight. We have to use dead weight pressure gauge. Now, what is the working principle as well as the diagram of dead weight? That's again a very simple. So here I am drawing dead weight pressure gauge. This is a test gauge that we want to measure. Anything, it can be diaphragm, it can be burden tube, anything it can be, right? And there is a chamber. I'm taking the chamber. Then we have oil reservoir. Now, do not ask me, sir, why there is oil, why not there is a water and all. That is a setup made by that particular person who made the deadweight pressure gauge. Right? We call deadweight tester. I'm not telling by myself. All these things are given in the Sinjal and Simbala. Again, I'm saying you are not believing that. You have to follow Sinjal and Simbala for ISRO examination regarding fluid mechanics and hydraulic machine. Even a single question, even a single question will not be skipped from that particular book in 2023 also, this year also. Again, we have the plunger and the pipe, and that's how the liquid will be coming. Again, we have the port here, we have the port here. Again, the oil will be coming here, and here we have the weight piston, and some weight has been kept, and this is the piston which is being reciprocating inside that, like this. When this particular oil is basically flowing in this reservoir, now this plunger is there for some purpose. I will be telling you this particular plunger. Now by default this oil will be here. Now when I open the valve, this oil will be start flowing, and the valve will be open, and this is start exerting the pressure, and you know that how the pressure will be measured. Let's suppose the pressure measured by this will be P oil by this test gauge, some X value, and this particular oil will exert the pressure onto here. And how much of pressure will be exerted? how much of pressure value will be exerted. That is weight plus weight of the piston, weight which I have kept, weight of the piston divided by area of the piston over which it is acting. Over which it is acting, that will give you the standard reading of pressure of the oil. Let's say y. If the y is an x, they are not equal. That means that test gauge is not giving you accurate value. When x is almost nearer to y, then we say that calibration is done, and whatever the testing is there, the test instrument is up to somewhat accurate now. Right. Again, some of you might be thinking, so why there is a plunger and this hand wheel is there. Now they are there for some purpose. When you start doing this experiment, the piston will be start moving downward and downward and downward. You will try to push this plunger in this direction, so that you are pushing the oil into these directions, in this direction, and that's how it exerts the pressure. And you will wait for the time where this particular weight as well as the pressure force by this oil will be balanced out. Till that you will operate this hand wheel. After that you will stop it and you will see, okay, now I have come across this come to the neutral condition where this oil force is exactly equal to the weight and piston force. Now I will stop. Once I will stop, I will be checking the value of pressure of the oil, and that is my reading of y kilopascal or anything in the units. That I will check when the liquid will be flowing in a burden tube, and the tube will be stretched, and then it will give the indicator reading, and that reading will be same or not, and that is how we do the calibrations, right? So this is your highly uh, accurate, high accurate pressure measurement device. So first thing. Second thing, it can measure very high pressure. It can measure very high pressure. Next time when they ask the same problem, next time is this time, 2023. Which of the following pressure gauge is generally used for very high pressure? Again, the answer must be C, right? Because you have to read everything. You have to read everything regarding dead weight tester from the Sinjal and Simbala, right? Dead weight directly saying you this dead weight which we have kept. Just on the basis of that, we are calculating the pressure. That's why the name has been given dead weight tester, right? Again, I have explained because uh, when you go to DRDO interview or ISRO interview, they will asking you, don't tell me the name, tell me the working principle of this, right? Try to solve this question. So take it the previous year questions very seriously. Do not take it granted that all the questions they are asking somewhat kind of a very simple questions, right? It's not like that. Again, velocity of this sound in a winter as compared to the summer will be higher or lower? Will be higher or lower? That you need to answer. When you follow speed of sound, when you follow speed of sound. In case of speed of sound, you know the formula under root of gamma RT, where R is nothing but RU divided by capital M. RU divided by capital M. RU divided by capital M. Now, I guess you must be getting the answer. Again, when the T will be higher, C will be higher. In case of summer temperatures are higher than winter temperature, then obviously C in summer will be more than basically what the VC of winter. So basically, which answer is correct? Velocity of the sound in winter will be lower as compared to summer. Again, that is the one question. Note down the next question. Question number two in the same here. Let's say this is a question number one in this 75, and this is a 75 second question. If I say, my dear friend, what we call velocity of the sound will be more in lighter gas or heavier gas. So when M will be more, R will be less. R will be less, C will be less. So note down velocity of sound will be more in lighter gas as compared to the heavier gas. So though that can also be asked as the question based on speed of sound. Remaining R we have explored, T we have already asked. Gamma, again, when you compare diatomic and triatomic gases, when this particular gamma will be gamma only. So again, gamma will be fixed 1.4. We do have gamma that is 1.4. So again, there is no question on that they will be asking. This is the question regarding 75th. Now note on the next question. Now coming back to this 76th question. Here you try understanding the particular question. Try understanding this question and tell me the answer. Now, my dear friend, here to explain this particular problem, a gas nitrogen is being expanded through a converging nozzle. It is being expanded from a reservoir to a converging nozzle like this. Let's say the inlet pressure and inlet temperature will be fixed P naught and T naught in this reservoir, right? And that is being given as zero point 0.5 megapascal. Now it has been expanded from zero point 0.5 megapascal to back pressure. Now back pressure we are maintaining here. We are maintaining some back pressure. What we are doing, we are maintaining some back pressure. Here we have connected nozzle. Here we are maintaining some back pressure. Once the back pressure will be start reducing, the mass flow rate will be start increasing. And you know that what is the value of that graph? How the graph will be plotted? Mass flow rate, per unit area. That is when we plot uh, back pressure divided by inlet pressure. We will be getting the graph like this. We will be getting the graph something like this. Now, what is this? What is this particular condition where the mass flow rate will become when you start decreasing the back pressure, when you start reducing the back pressure, generally the mass flow rate will be start increasing because driving force will be start increasing. But you reach certain condition where we call P star by P naught, that is called choking condition. Here you will get further you reduce the pressure, mass flow rate will not reduce, that will remains constant. Mass flow rate will not increase. You further reduce the back pressure, that particular pressure will be called choking, choked pressure, and that maximum mass flow rate condition will be called here. The nozzle gets choked at this point. The nozzle gets particular choked at this particular point. Let's calculate what is that P star divided by P naught. You know the value. What is the value what is the formula which we calculate here? P2 by P star by P naught. That is, we have the formula 2 by gamma plus 1 divided by gamma minus gamma 1. Not only they asked this particular question, not only they have asked this particular question, but they also ask the next question. When you see, they ask critical to stagnation pressure ratio. Again, they ask the formula also based on that, right? So again 78, what is the answer? 78, again the answer must be again C. But I'm saying you, not only they ask the question on that, they are asking formula also. So again, overall they ask for 6 marks, right? Now P star, P naught already we know 0.5. A for the air we know gamma for the air. Oh sorry, for the nitrogen. Again, nitrogen is also diatomic gas, that is 1.4. So 2.4, 1.4 divided by zero point 0.4. So my dear friend, when you calculate the value of P star by P naught, what you will calculate? 1.4 divided by zero point 0.4. 2 divided by 2.4. Point 264 megapascal. That means this particular pressure is 0.264 divided by something like that. Now they are saying they are saying that it has back pressure has been reduced from zero point 0.1 megapascal to zero point 0.4 megapascal. 0.1 megapascal to zero point 0.4. That means somewhat here. 0.1 divided by 0.5 to 0.4. 0.4 means somewhat here. Because this condition, you know that. This condition, you know, that is a choking condition. Now, you got the every point. Now read the problem. If the back pressure is increased, that means we have to go like this. If the back pressure is increased from zero point 0.1 to zero point 0.4, the mass flow rate trending will be like what? So generally, if I plot mass flow rate simply, not per unit area, so what I am getting, first of all, the mass flow rate will remain constant up to the point of choking condition, then further it will reduce. So which option is correct? Mass flow rate will remain constant till a point, till the choking will happen, and further it will gradually decrease. C option will be correct. Right? Make a note of it. Further, we will see the derivation of this particular formula. We will see the derivation of this particular formula. Make a note of it. Once it is done, we can move on to the further next question. This is what you have, a reservoir. Now the next particular problem, they are asking critical to stagnation for an expansion process which are happening in a particular nodule, for example. Now we got the answer as C, no problem. We got the answer, sorry. P star by P naught will be 2 by gamma plus 1. C and D looks like a same here. P by P star by P. Now that is 2 by gamma plus 1 the whole to the power gamma by gamma minus 1. So C and D looking like a same option. So both will be correct. Now here, what is the proof of that? First of all, we will understand what is the meaning of stagnation properties. Right? Stagnation means you have certain, at any point you have enthalpy, internal energy. Internal energy. You have certain velocity, certain enthalpy. Whenever the flow will happen, certain location where the velocity will be zero, at that particular point, everything will be converted to stagnation property. H will become H naught. U will become U naught. Then what is the formula we will write, my dear friend? The formula we will write here, H, you know that steady flow energy equation where heat transfer is zero, work done in control volume is also zero. So we can write H1 plus V1 square divided by, again we are writing, for example, we are writing 2 H2 plus V2 square divided by 2, and here we will be writing H01. This we are writing H01. This we are writing H02. That is a stagnation enthalpies. So what is the H01? H01, my dear friend, we can write here this as Cp T01. That is equal to H1 plus V1 square divided by 2. Can we write T01? That is equal to this Cp into T1 plus V1 square divided by 2. Here T01 we can write T1 plus V1 square divided by 2Cp. We can write 2Cp. We can write 2Cp. Further, what we can write, my dear friend? Here, what is a T01 divided by T1? T01 divided by T1. 1 plus V1 square divided by 2Cp into T1. Into T1. This thing we can write. Further, what we can write? Further, what we can write? How to simplify here? How to simplify? See, we know that V square can be written as C square M square, Mach number. So further we can write T01 divided by T1, that is equal to 1 plus, here understand, V1 square we can write C square plus M square divided by 2Cp into T1. C square we know that gamma RT, so this we can write T01 divided by T1, 1 plus gamma RT1, that will become M square divided by 2Cp1, 2Cp, 2Cp. Further, what we can write? Further, this T1 and this particular T1 will cancel out. This particular T1 and this T1 will cancel out. Cp what we can write here? T01 divided by T1, we have written something like 1 plus, let me just check, gamma R M square divided by Cp, sorry, Cp into T1, 2Cp into T1. T1 cancel out. Cp we know that R gamma by gamma minus 1. R gamma by gamma minus 1. So T01 divided by T1 we can write 1 plus. 1 plus. What is the value? Gamma and gamma will further cancel out. Gamma minus 1 divided by 2 into Mach number square. That is a particular thing we have calculated. Now, my dear friend, whenever we have certain case where this is a state number 1, T01 corresponding to T1 is corresponding to what we call state 1. Then what about T1 star or T star will be corresponding to the value of what we call sonic condition. Sonic condition. So what is the sonic condition? Let's say here we have the Mach number, certain Mach number. Now you are basically what you are doing. You are just expanding till the point of critical condition. Critical condition means what is the critical properties? T star, rho star, P star. These are the critical property. These critical properties are calculated at sonic condition at Mach number equal to 1. At Mach number equal to 1. Now, when you calculate T0 1 by T star 1 plus 1 square, because Mach number should be 1. When you convert T1 star to T1 to T star, there has to be Mach number 1. Then T0 1 divided by T0 1 divided by T star will be how much? Gamma plus 1 divided by 2. Getting my point? So this is a particular value which we got it. Now they are not asking this question. They are not asking this question. They asked the problem corresponding to pressure ratio, pressure of critical to stagnation. So what we can calculate here, simply we can write T naught divided by T star, that is equal to gamma plus 1 divided by 2. Now, when we got this particular value, then we also know one more relation for isentropic process. What we know for our isentropic process? We know for our isentropic process, T naught 1 divided by T1, that is P naught 1 divided by P1 to the power gamma minus 1 by gamma. This particular relationship, we know that. Similarly, my different T naught divided by T star can be written as P naught divided by P star to the power gamma minus 1 by gamma. Can we write like this? Yes, very well we can write. We have to calculate P naught star, P naught divided by P star, that we can write T naught divided by T star to the power gamma divided by gamma minus 1. So what we can write, my different here? P naught divided by P star, that is gamma plus 1 divided by 2 to the power gamma by gamma minus 1. But in the problem they have asked P star divided by P naught. Then answer must be 2 by gamma plus 1, gamma divided by gamma minus 1. This answer must be correct. This particular answer must be correct. You can see P star by P naught. From here to here, what? Why I have written T naught 1 to T naught? Because I have just denoted T naught not to any other 1, 2, 3, 4 state. Just the stagnation to is critical. Make a note of it. You also know that P uh, PV to the power gamma, that is equal to C. That thing you know. For a specific volume, we can also write P by rho to the power gamma equal to C. That everyone know that. So here we can also write P star divided by P naught divided by P star, that is rho naught divided by rho star to the power gamma. So if you want to calculate rho naught by rho star also, that also you can calculate. How much of value? Gamma plus 1 divided by 2, gamma plus 1 divided by 2, 1 upon gamma minus 1. That will be the answer. So we have not only seen the values of what we call uh, critical to stagnation temperature ratio, critical to stagnation pressure ratio. We have also seen critical to, or we rather to say critical stagnation to critical density ratio, right? Please make a note of it. All these things are very, very important. This relation, and this particular relation. Or you can also write rho star by rho naught, that is equal to 2 by gamma plus 1 to the power 1 upon gamma minus 1. Density ratio, that they can also ask. Right. So very quickly, we will go through the last particular problem. This is a problem regarding the Pelton turbine. Read the statement for next 1 minute. Read the particular statement for the next 1 minute. It's a very simple, straightforward question. For a maximum efficiency, we know that velocity of what we call speed of a blade should be v1 divided by 2. Proof I will give in the next class, right? But right now we will prioritize our solution. What will be the answer for this question? For a maximum efficiency, this should be the condition. For maximum efficiency, this particular thing should be the condition for a Pelton turbine. For a Pelton turbine, U is what? Pi d n by 60. Velocity of the flow is not been given, but we know that velocity of the flow, which is flowing, this is a turbine, right? Pelton turbine, tangential flow turbine. V1, we know that Cv into under root of root 2gh. Cv is what? Coefficient of velocity. It is not given. You take it as 1. So V1 can be calculated as under root of 2g into 126. Now you know that pi d n is what? 2000 divided by 60. That is equal to 1 upon 2 times of under root of 2 into 9.81 into 126. So my dear friend, when you calculate how much of value you will be getting, you will be getting diameter as 0.237 meter. When you approximate to this, you will be getting 23.7 centimeter. That means 24 centimeter. Please make a note of it. Once it is done, we can leave for the day. That's a very simple proof is there. You can also do the only thing in proving this one, we have to vary which thing? We have to vary for a given u value. See, velocity of flow will be fixed, that you cannot change, but speed of the bucket, that you can change. So this is a variable. So definitely you have to differentiate efficiency with respect to u only and equal to 0, right? Whenever we have to differentiate with respect to the variable parameter, not with respect to fixed parameter, right? No doubt. Okay, thank you.